Girls, we're looking at 2017 B1 now for this part. It's a slightly unusual one. So we've had a look at 2017 part A. So part B is about a spacecraft moving in a straight line towards the centre of the Earth. It says the radius of the Earth is r, and when this spacecraft is at a distance x from the centre of the Earth, the force exerted by the Earth on the spacecraft is directed towards the centre of the Earth and has a magnitude of k over x squared. So you've got to show that k is equal to mgr squared. So this is 2017 10b. Okay, so this, just straighten that out. Is that okay there? It is, isn't it? Yes. So 2017, this is part B, 10b. Okay, so let's see, what do we know? So we have this space, we have the centre of the Earth, and we have a spacecraft somewhere out here, P. The radius of the Earth, it says, is r, and this is the centre of the Earth there, O. And it says it's at a distance x from the centre of the Earth. Okay, so let's have a look at the forces acting on that particle. So the forces acting on that particle, it's just got a weight force at the moment, which of course has to be, well, if it's a weight force, it's going to be directed towards the centre of the Earth. So there it is, mg. Now, I don't know if you can see that, I'll put it in red. So that's mg. Now then, so what's the F nets on this? And it's remember, this is moving towards the centre of the Earth, so that spacecraft is acting towards the centre of the Earth. That would be the direction of the acceleration. So what are the F nets? The F nets, of course, there's only one, which is the weight force, mg. And it tells you in the question that the force exerted on this spacecraft is k over x squared. And the weight, of course, is acting towards the centre of the Earth. So I'm going to put this mg, F nets equal ma, equal to k over x squared, and then say mg x squared is equal to k. And of course this force that's acting is acting a distance of r from the centre of the Earth, because the radius of the Earth is r. So I'm going to say this is mg r squared is equal to k. So that tells me what the first part of the question is. Okay, so I've shown that. Now, the second, I'd make that work, girls. If it didn't, I'd make it work. Okay, P starts from rest when it is at a distance of 5r from O. You've got to find, in terms of r, the speed of P as it hits the surface of the Earth, and there's no resistance. Okay, so what have we got here? We've got this spacecraft coming in. We want to find its speed. Starts from rest. We want to find its speed as it hits the centre of the Earth. Now initially we'll call the distance out x, so it's at a distance 5r from the centre of the Earth. And of course when it hits the Earth's surface, it will be at a distance r from the centre. Okay, the other thing is I've got to remember that this spacecraft is coming in towards the centre of the Earth, so it is a retarding force. So the Earth is issuing a retarding force because this spacecraft is slowing down as it approaches. So this spacecraft P is slowing down as it approaches the centre of the Earth. Okay, so I'm going to say that I know what my F nets are. F nets equals ma. My F nets are k over x squared, that's what I'm told in the question, is equal to ma, and it will be minus ma because it's retarding, it's a slowing down force. I've already shown what k is. It's mg r squared over x squared is equal to minus ma. I'll get rid of those m's, so g r squared over x squared is equal to minus a. Look at my limits now, they're in terms of v and x distance, so I'm going to change that a to a dv dx. So this will become gr squared over x squared is equal to minus v dv dx. I'll separate the variables. Gr squared is a constant, So gr squared dx over x squared is equal to minus v dv. And then I'll leave that gr squared out. So I'll integrate both sides. So I'll integrate this, that's a constant, integrate this. Right, what are my limits going from? They're going from 0 to v on the velocity side and 5r to r on the distance side. So let's integrate this. So the gr squared, of course, is a constant. This will be x to the minus 2 dx is equal to minus v dv. When I do this, so I'll move up over here. So this becomes gr squared. I'll integrate this and it will become minus 1 over x. And that's equal to minus v squared over 2. And of course, again, my limits are going from 0 to v. And this one is going from 5r to r. So I'll say that this is minus gr squared. I'll bring out that minus over here. Minus gr squared, and that will give me 1 over 5r minus 1 over r when I put in my limits. And that's equal to, I'll bring out that minus a half, and this will become 0 minus v squared. So minuses on both sides will cancel. Gr squared, when I subtract those, that will become 4/5 of r over r, 4 over 5r, is equal to a half v squared. And this will become, of course, that will be minus. So that will become a plus. Sorry, there's a plus. This will be a minus and a minus here. This minus will cancel with that minus there. That would be a plus. So this gives me then 4/5 gr is equal to 1/2 v squared. So when I sort all that out, I'll get 8/5 gr is equal to v squared. So v will be the square root of 8/5 gr. Okay.